Okay, let's dive right in and crack open a classic. Problem 1.98 from Irodov's legendary physics book. If you've ever worked through these, you know they can be a real challenge. But man, is it satisfying when you solve one. So today, we're going to tackle one together. You know that feeling, right? You're staring at a problem and you just have no idea where to even start? Well, if you've been there, you're in exactly the right place. We're going to build a solid, step-by-step method to turn that confusion into confidence. All right, so here's the challenge we're up against. We've got a particle, it starts from a complete standstill, and then it gets pushed by this force that goes back and forth, kind of like a sine wave. Our job is to figure out exactly how far it travels over time and then get a rough idea of what that journey looks like. So how in the world do we get from a force all the way to a distance? It might seem like a huge jump, but there's actually a very clear path that connects them. Think of it like a roadmap, and we're about to follow it step by step. Here's our game plan, our four-step attack. First, we'll use Newton's law to get the acceleration. Then we'll integrate that to find the velocity. After that, we integrate again to get the distance. And finally, we'll take a good look at our answer and sketch out the motion. Simple as that? Let's get started. First things first, we need to connect the force we're given to the particle's velocity. This is really the heart of dynamics, right? Understanding how forces actually create motion. And our journey starts with the one and only, the cornerstone of mechanics, F equals ma. Now, remember, acceleration is just a fancy way of saying the rate of change of velocity. So we can rewrite this as F equals m times dv over dt. This is perfect because it directly links the force we have to the velocity we want. So what we do is we take that specific force from the problem, the F0 sine omega t, and we plug it right into our equation. With a little bit of rearranging, we get this expression here. And look at that. To find the velocity, v, all we have to do is solve this integral. This is where calculus becomes our most powerful tool. But hold on. Right here, this is a classic trap. So many people forget this next part and it throws the whole problem off. Whenever you do an indefinite integral like this one, you absolutely cannot forget to add that constant of integration, that plus c. It's not just some mathematical rule. It holds a real physical piece of information about our problem. So how do we find this mysterious c? Well, we look for clues in the problem statement. And we have a big one. The particle starts from rest. That means at time t equals 0, the velocity is 0. We can plug those initial conditions right into our equation, and that lets us solve for c. Turns out it's f0 over m omega. And boom, there it is. We substitute our value for c back in, and we've got our complete velocity function. This beautiful equation tells us exactly how fast our particle is going at any moment in time. All right, we have the velocity, so we're making great progress. Now we can move on to the next step, finding the distance. And you're probably thinking, great, another integral. And you're right, but not so fast. First, we have to think about something really important. Before we just blindly integrate again, we have to be really clear about what we're actually looking for. Are we finding the displacement or the distance? Remember, displacement is just your change in position from start to finish. But distance is the total path you took. They're only the same thing if you never, ever turn around. So that brings us to the key question, does our particle ever turn around? In other words, does its velocity ever become negative? Because if it does, our calculation for distance gets a lot more complicated. We'd have to find when it turns around and add up the different parts of the journey. Let's take a closer look at our velocity equation to find out. This first part, f0 over m omega, that's just a bunch of positive constants. So the real action is in the parentheses, 1 minus cosine omega t. Now think about it. What's the range of a cosine function? It only goes between -1 and +1. So what's the smallest that 1 minus cosine can ever be? 0. It can never, ever be negative. And that, right there, is a huge deal. It's a critical insight. Because the velocity is never negative, our particle never moves backward. It might slow down, sure, but it's always chugging along in the same direction. And that means our job just got way easier. The distance it covers is exactly the same as its displacement. Okay, now that we've confirmed that, we can set up our final integral with total confidence. The distance, s, is simply the integral of that velocity function we worked so hard to find. So let's solve this thing and get our final answer. So we've done all the heavy lifting with the calculus and the conceptual checks. Now it's time for the payoff. Let's look at the result of that final integral. And more importantly, let's figure out the story it tells us about how this particle is actually moving. And after all that work, here it is. We integrate our velocity function, we apply our initial condition that the distance is 0 when time is 0, and this is what we get. This equation gives us the exact distance the particle has traveled as a function of time. Now, okay, we've got an equation. That's great. But what does it mean? What does this motion actually look like? It's clearly not constant speed and it's not constant acceleration. So what is this particle really doing? The best way to understand this is to break it down into two parts. See that omega t term? That tells us that, on average, the particle is just drifting forward at a steady rate. But then you've got that minus sine omega t term. That part adds a little wiggle, an oscillation, right on top of that forward motion. So it's always moving forward, but its speed is going up and down, up and down. And if you look at this plot from the book's answer key, you can see it perfectly. That overall straight line upward slope, that's the steady drift forward from the omega t part. And those little wiggles on top of the line, that's the sine part, showing the speed fluctuating. The particle is always moving forward, but it's constantly speeding up and slowing down in this perfect repeating cycle. And that's really how you do it. You take a complex problem, you break it down into logical steps, and you check your reasoning along the way. Now, to really test your understanding, here's a little challenge. What if that force was a cosine function instead of a sine function? How would that change things, especially that crucial first step? Think about it. It's a great way to make sure you've really got this down.